For my standard 6.2, I chose to do problem 6.33 from the book. It asks us to show that the tunneling probability through a barrier of width d is proportional to e raised to the negative 2 qd, for qd is much greater than 1. So here is a drawing of a barrier, a potential barrier, and the width is 2a, or we can call 2a equal to d. On page 190 in our textbook, we are given the tunneling probability through a square potential barrier described as this. So the potential is 0 outside, and inside the barrier it is equal to V naught. So to find the tunneling probability that is given on page 190, well, first let's talk about what quantum mechanical tunneling is. Quantum mechanical tunneling is the quantum mechanical wave function, is when a quantum mechanical wave function penetrates into the classically forbidden region. This is responsible for radioactive decay and the current in high frequency semiconductor diodes. Quantum tunneling has an optical analog where a light wave penetrates into air while being totally internally reflected from inside a glass prism. So anyway, to solve for our tunneling probability, we can start with the separate eigenvalue equations of the different regions, which are shown here. So inside the region, our potential is equal to V naught, and outside, using our constants Q and K, where K is a wave vector and Q is a decay constant, we can rewrite these as this. Then the general solutions to these are shown here, where A, B, C, D, and F are all amplitudes. A, the coefficient A represents the amplitude of the incoming wave. B is the amplitude of the reflected wave. F is the amplitude of the transmitted wave. And C and D are the amplitude of the waves inside the barrier. So the boundary conditions for the continuity of the wave function and their derivatives are shown here. To solve, we want to solve for F and A, because the ratio of F over A is the amplitude of the transmitted wave to the amplitude of the incoming wave. And then we want to find the absolute square of this ratio, and this gives us the relative probability T that an incident particle is transmitted through the particle well, and this is called the transmission coefficient. So solving for the ratios of these amplitudes, we can get the transmission probability, which is shown here. And we know that A is equal to 2D, so we can rewrite this in terms of D. And we can write sinh of x, since it's the hyperbolic equation, as e to the x minus e to the negative x over 2. And when x is much greater than 1, this is equal to e to the x over 2, or approximately equal to e to the x over 2. And then plugging that in and doing a little algebra, we can see that the transmission coefficient is proportional to e raised to negative 2 qd. Since these are constants, this is e to the negative 2 qd, and this is my standard 6.2.